The second part of the lecture in chapter 12 deals with the concepts of buoyancy and Bernoulli's equation, which is a type of energy conservation for fluids. So first off, that word buoyancy. See, I told you I even hate how it's spelled. Look at this, U-O-Y. What kind of word has U-O-Y in it, right? That's just a messed up word. All right, so the idea with buoyancy is we're considering if an object is submerged in a liquid, what will it do? Will it sink? Will it stay in suspension in the liquid? Will it float? And so that's what we're interested in doing here. So if we look at an object that is submerged in a liquid, okay, so we just kind of freeze time here. We look at the cylinder that's submerged in the liquid. You want to ask yourselves, what is going on with it? Well, we're going to use a cylinder as an example because a cylinder has a nice illustration as to how the forces and pressures will work here. What we learned in the last lecture about hydrostatic pressure is that it increases with depth. And so what that means for the cylinder is that the force that's exerted on the top of the cylinder that points downward will not be as great as the force that points upward because there's greater pressure underneath it. And the difference between those two forces, the force that points down and the force that points up, is what we call the buoyant force. And that is ultimately going to determine if our object is going to sink, be suspended, or rise. Okay? So how do we determine that stuff? Well, you have to imagine that any difference that's going to exist there is going to be the result of fluid that would normally be there, but has been displaced because the object has been put there. So on the left here, we have this sort of imaginary boundary. Imagine that, we just imagine a cylinder, for example, or this irregular object that we have here. And we consider the forces that act on it. If we look at the liquid that's represented by that boundary, well, the liquid is basically in suspension because what happens is we have the weight of the layers pushing downward and we have this force pushing upward, which is a result of the pressure there, and so it stays still. If we take a real object, though, and put it, what happens is that real object displaces fluid. And it's really going to come down to how does that displaced fluid compares to the new material that is there. If it is denser, we would expect it to sink because the gravitational weight is going to be bigger than the buoyant force, okay, bigger than the upward push, right? And if the density is less, we would expect that gravity wouldn't be as large because now if it's less dense than the water, then the volume that's there doesn't contain as much mass as it did before. And so that actually is going to make the object rise. So when we're considering submerged objects, you're kind of imagining, how does the object that is present there compare to the water that would be there if it wasn't there? And that really helps you understand how this is going to behave. Well, let's actually put some numbers behind this stuff here. Okay. So what we're considering is this. When an object is immersed in a fluid, the displaced fluid's volume, okay, is going to equal the volume of the fluid, obviously, right? So if it's a cylinder, there was a cylinder of water there that's now been removed, and instead, in its place, we have this object here. And we have a principle that explains this we call Archimedes' principle. And what it says is that a fluid will exert an upward buoyant force. Remember, that's a net force on an object immersed or floating in the fluid. Now, the magnitude of this net force is going to equal the weight of the displaced object. That's the object. That's the idea here. So it really comes down, like I said, to a matter of density. If we want to express this in a form, if we want to express the buoyant force in a form here, it would be equal to the basically the mass of the fluid that was displaced times gravity. That would be the gravitational force. But we're going to put it in terms of density and volume. So we're going to have here rho v, that's equivalent to mass, times g. And that really represents our buoyant force. Now remember, that's a net force. So you imagine that there's a weight that sort of pushes down, right, on the top. And there's a weight, and sorry, there's a force that pushes down on the object, and there's a force that pushes up. Well, if you analyze the hydrostatic pressure at those, the difference between those is going to be this rho GH. That's the idea. Rho GH is the difference between this stuff, and that's the pressure. Well, let's look at that. Let me write it out here. So now, in considering the hydrostatic pressure at the top and below, we can take out atmosphere because they both experience an atmospheric pressure. And so that we find that the difference here is that the pressure, I don't want green. Let's do red. Okay, that the difference in the pressure here, right, is going to be equal to rho. I'm going to write it out like rho. Rho, that's density. I can't really do a Greek letter very easily here. Times G times H. Well, what's pressure? Pressure is force over area, right? And that's our rho times G times H. Okay, so that's basically the difference in pressure that exists from the top to the bottom. When I'm going to write the pressure in terms of force over area, I multiply both sides by area here. I combine the area with the H, and that's a volume. And so that's how we end up with the equation over here. But you can also interpret it as we're looking at the mass of fluid that's displaced here. Okay, so that's how we consider what the buoyant force is going to be on something that is submerged. Okay. All right, so consider this. A heavy lead block and a light aluminum block of equal sizes are both submerged in water. Okay. Now, when I say submerged, we'll just say that we forced them under the water. These things are, we're not going to consider the fact that, maybe these things float. They're under the water, but all right. They would sink, but, whatever. But that's not important for this. So which one is going to have the greater buoyant force? Right? Think about this for a moment. But the answer here is going to be C. If they're submerged underwater, then they both displace the same volume of water, which means it's the same weight of the water. So if I go back to the buoyant force here, this is, now look at the subscripts, rho F, rho V. We're talking about the volume and the density of the fluid that's displaced. Obviously, that will be the same volume as the object itself. And of course, the fluid is water. It's whatever the density of water is. So buoyant force will be the same for these two things, right? Now, there's some difference between the blocks, but in terms of being submerged, the same upward force is exerted on these things because they both displace the same volume of water. That's the idea. Let's go ahead and just get right to an example here. Now, we're going to have a block of wood here. Now, a block of wood is less dense than water, and as a result of that, would float on the water. And so what we want to consider is we want to work out what the buoyant force is here. Now, we have to submerge this block of wood, and normally it wouldn't be submerged. So we're going to tie it to a rope that's in the liquid here. And we want to figure out what the tension would be. Now, the buoyant force is going to be larger here than the gravitational weight of the object. The gravitational weight of the object is going to be mg, which would be like rho v, but for the wood. And the buoyant force is going to be rho v for the water. Now, because the density of the water is greater, the buoyant force is larger than the gravitational force down. So the difference between them is going to be the tension. But let's go ahead and look at the example here. Here we go. All right, so look at this right here. This is nice. Right up here. Check this out. The buoyant force is how we defined it. It's the density of the fluid, volume of the fluid, times g. This is the gravitational force of the water that was displaced. That weighs more than the same volume of wood. The gravitational force of the wood is rho wood, V wood times G. Now, what's the difference in these two equations here? G is the same, V is the same, so what's different? Densities are the same. Now, if these two things are equal to each other, then F net is 0, and this thing will simply be suspended. But that's not the case here. The fluid has a much larger density, so the buoyant force is larger. So if I do my summation of forces in the y direction, I get the buoyant force going upward, I get my weight going downward, and I have an additional tension that's holding the thing down. Right, so we're going to take a difference here. I'm going to solve for t. We're going to have our differences here, okay? And I'm basically just looking at the difference of densities. The difference of densities here, right, times the volume, that's a cube, 10 centimeters on a side. And so I work out what the difference in the densities are. My volume, 0.1 cubed, G is 9.8, and we get 2.9 newtons. That's what the tension is to keep this thing submerged under the water. Okay, but the key to this is this little relationship up here. That's the key, and this is going to be very important for understanding how things are going to behave when they're in that liquid. All right, so if the, now again, when I talk about these next few things here, go back to that example and look at those two equations I have there. What's the buoyant force? What's the gravitational force? Okay. So, our object's going to sink, be suspended, or float. Well, as you can already see from our discussions here, it's a matter of density. Okay. An object will sink if the volume of water that it displaces weighs less than the mass of the object. Okay, and that's really and the volumes are the same if you're submerged. So this is really a matter of densities. If the density is greater than the density of the fluid, it will sink. It will float if the density of the object is less than that of water, because you're displacing fluid, but you're putting an object there that weighs less than the fluid that would be there, and therefore the buoyant force is going to be greater than gravity, and the object is going to rise and float on the top. And we'll deal with what exactly happens when we float on the top in a moment here. What we call neutral buoyancy, or being simply suspended in the liquid, is if somehow you've created an object that matches the density of the water. Okay, and this is something that you can easily replicate if you ever, when you're in a pool as a kid, or maybe now, you can control if you can sink or float by changing your density. And you change your density by taking in air into your lungs. If you remove a lot of air from your lungs, you can make yourself effectively heavier. That allows you to sink. But however, if you take a lot of air into your lungs, right, you'll float. And then if you submerge yourself underwater, you can release enough air to the point where you're basically in suspension. So you can, with your lungs, you can modify your density, and you can produce any of these effects here. But ultimately, you're going to be suspended if your density matches the density of the water. All right, so we got two blocks of identical size. One is made of lead and sits at the bottom of the pond. The other one is wood and floats on top, upon which is the buoyant force greater. All right, so think about that for a minute here. Remember, the definition of buoyant force is the density of the fluid, the volume of the fluid, and G. Okay, the answer here is A, lead block. Why? Because if you look at the buoyant force equation, there's a VF in it, volume of the fluid. And that's the volume of the fluid that is displaced. The lead block displaces its volume in fluid, whereas the wood only displaces some of its volume in fluid. Okay, because say the block is, say, half submerged. Well, it's only displacing that amount of fluid, which is not as much as the lead block, assuming they start from the same size. What is the wood block doing? The wood block turns out to be displacing enough fluid that matches its gravitational force. Okay? And so that's why some of it will float above the water, and we're going to look into this for a minute here. But this is really the kind of the keys to submersion and floating. Objects that submerge displace water equal to their volume, where objects that float will displace water equal to its weight. And that is something you have to figure out for objects that have densities that are smaller than that of the fluid that they're submerged in. Okay, moving on. All right, so let's actually look at what happens when objects float. Now, when objects float, obviously, they're in a static equilibrium. So F net is 0. So that means the weight of the object that is pushing down, right? Let me get that up here. Weight of the object pushing down is this m naught g, right? And that has to be equal to the buoyant force that supports the object. And so that's going to be rho f vf g. Well, if I take my mass here and write it in terms of volume and density, I get this other expression right here. And because they're in equilibrium, these two quantities are equal to each other. Cross out the g's, okay? And we end up with this nice proportion down here. This proportion is really helpful in helping us understand how much of the object gets submerged. So if the volume of your object is less than the volume of the fluid, this ratio of densities is less than 1. And that means the volume of the fluid that's displaced will be less than the volume of the object, right? And that means a certain percentage of it will lie above the water. How much would that be? Well, it's a matter of writing out these volumes in terms of the areas times the heights. So you can, in fact, replace these V's with A times H, for example. And that can tell you how much higher above the water it is from water level. And I'm going to do some examples so you see how that works. Let's just get to those then. Example here with an iceberg. That's a nice iceberg. Last lecture I didn't have a nice iceberg there. It was kind of weird looking. So I did a better job this time. Got you a good iceberg. Where is... Here we go. Okay. So the idea, again, is that the buoyant force is equal to the weight of the object. The buoyant force is the volume of the liquid, the density of the liquid, the volume of liquid that is displaced, which is not the full volume of the object, just the volume that's displaced. And then, of course, for the ice, this is simply the density of the ice, the volume of the ice. That's the full volume of the ice, by the way. And so we cross out the g's and we're going to create a proportion here. Displaced volume over the total volume of the ice is apparently going to be equal to the ratio of the density of the ice over the density of the water. Salt water is what we're going to use here. Ice has a lower density. It's 917 kilograms per cubic meter. The salt water is going to be 1,030 kilograms per cubic meter. And with this ratio, when you multiply that by 100%, we get the ratio is 0.89. As a percent is 89%. And so what this means is the 98% of the iceberg is submerged. And the reason why so much is submerged, that's the whole tip of the iceberg kind of talk, figure of speech, I should say, that people use, is because the density of the iceberg is so close to the density of the water that's submerged in that most of it is submerged. And where a small portion's up. And for icebergs, generally, you're talking 90% or so. And that's why. It's basically because the densities are so close is why that happens. Which is unique because usually solids are more dense than water, so most things float, but water's special. And it tastes good too. Let's get back to the lecture. All right. So, if you look at these examples here, you want to ask yourself, which floating block is the most dense, right? Let's think about that. All right, so the answer here is A. Why? Because, again, ratio of volume, ratio of the density. If there's a greater volume under the water, then it's closer in density to the fluid. B and C looks like B is probably the least dense, because a greater percentage of its volume is above the water. C is a little bit less. It looks like maybe 40% or so is above the water. For B, it looks like it's like 60 or 70 or something. A has a lot of its volume under the water. So if you had to rank them, B is the least dense, followed by C, A being the densest. Okay, fantastic. Right. Blocks A, B, C are all the same size. We want to know which one experiences the largest buoyant force. They have different masses. Keep that in mind. Okay? Well, at least one does. Different masses, different depths. The answer here is they all have the same buoyant force. Why? Because they're submerged. Because they're submerged. And the buoyant force is equal to density of the fluid, volume of the fluid that's displaced, times G. And all these objects are in the same liquid. They displace the same amount of volume. And they're all on Earth or some other planet or whatever, but it doesn't matter. All the G's are the same. Okay, great. All right, so this brings us to the concept of a boat. Okay, so the idea with the boat is that we take advantage of this principle here. Okay, and what we're trying to do here, and let me sort of explain how this is working here. The boat is the idea behind the boat is that it's going to have a very large surface area to it and a small height to it. I mean, when you see boats, they have a very large, sort of almost flat bottom to them, because you're trying to do this is in order for the boat to float, you have to have its average density less than that of water. You can obtain that if you can create an enormous amount of volume that just has air in it. Okay, and so the idea behind this is we're doing buoyant force stuff. So let me write this out for you. Okay, so the buoyant force, right? That's going to be buoyant force here is going to be rho for the liquid times the volume of that's displaced, right? And times G. And we know that is equal to, if the object floats, it's going to be the mass of the object times G. So we're saying the buoyant force is equal to the weight of the object here, right? Well, for the volume, let's just say that volume, we'll do a simple boat here, a rectangular box or so. So it's going to be area times H. H is the sort of the height of this thing. The G's drop out here, and so we're just left with this relationship here. Solve for H, and that's how we get the equation over here. And this will basically tell us, what's the minimum height that the sides need to be for us to be a legitimate boat here. So it's the mass of our object divided by rho A, where A is the surface area, right? And so if you create a really large surface area here, right, that makes this ratio small, and so H can be small. And so you don't want H too high because you could have an issue with gravitational torque, things can topple over. So you actually want to create a really small height to support the object. But here's the same principle. We're just equating the weight of the object with the buoyant force. And if we just treat this object as a simple shape, then we can easily figure out a minimum size to support our object here. And so that's what we're looking at here. All right. And then, of course, you can figure out, how much further down is it. It's really, it's the same thing. It's like the ratio of volumes is also the ratio of heights. So if you know your density, your ratio of densities, you can figure out a ratio of heights. Like if we talk about the iceberg there, right? You can have 10% floating above water and 90% underneath it if you have the densities, at least for the densities of the iceberg. So that means you can kind of create whatever height you want depending on what kind of area you want to choose. That's the idea. All right. Let's get to another example. Where is right here? Okay. We want to determine the density of an unknown liquid. We notice that a block floats in this liquid with 2.6 centimeters of the side submerged. Okay, Well, in water, the block floats with 5.8 centimeters submerged. Okay, so the block is floating in both circumstances, right? So we're going to do the same exercise we've been doing, and the key to things that float is trying to maintain this relationship. Buoyant force equals gravitational force. So for our unknown liquid, we can create that. We have the we have the density of the liquid, unknown liquid, times the volume of the unknown liquid, that is submerged, times G. And then we have on the right-hand side our density of our block, volume of the block, that's volume above and below, right? It's the whole thing. And we do the same for water, right? And so, you know, the right-hand sides, as you can see here, they're the same. It's the same block, right? So that means we can equate the left-hand sides. So the left-hand sides are equated together. Now, what we're doing with this block here, and I'm treating the block as if it's literally a rectangular box. So the volume is going to be the area times the height, and this height is the height that is submerged, right? And so we equate those two together. The A's drop out, the G's drop out, and we get what I described in the last problem here. You end up creating a ratio of, well, proportion of density and height. So we solve for the unknown liquid's density, and we find that the density of this is more than that of water. It makes sense because we have less of it submerged here. So in the water we have 5.8 submerged, but in the liquid we have less. So that means more must be above the water, and that would occur if it's denser, right? And so we get 1,260 kilograms per cubic meter here. Okay, good. Fantastic. Back to it. All right, so that was buoyancy. Next topic is fluid dynamics, which we just skim the surface of. That's kind of a pun, but I didn't mean it that way. But we do. We just kind of barely get into this topic here. We make a lot of assumptions in fluid dynamics. Fluid dynamics is filled with lots of assumptions that attempt to simplify the work that we do. Okay. And some of those things are the fact that our fluid is going to be incompressible, non-viscous, and steady. And what do these things ultimately mean here? Non-compressible means, now, just to give you a heads up here, everything we're going to talk about in this section is energy arguments. So I'm going to just start off by telling you we're doing energy arguments, okay? Energy arguments are going to want certain conditions. The fact that the fluid is incompressible, so it's going to behave more like the gas, more like the liquid than the gas we've been dealing with, is ensuring that there's no external work done on the system. You know, we can definitely incorporate the fact that the fluid can be compressible, but it adds a layer of complexity, and basically it requires us to add in external work, which we don't want to do, but just do the basics and first figure that out before we do anything more complicated. We also want the fluid to be non-viscous, which is our way of basically saying there's no friction. Okay, because friction is a dissipative force, and that's going to remove energy from the system. And then the other one is we want flow to be steady. Now that's a little bit outside of the other things there. Let me explain a little bit about what we mean by steady flow. In the example here with these little sticks, these little fuses, so to speak, we see two different types of flow here. We see what we call turbulent flow and laminar flow. Laminar flow is very smooth and very even, and turbulent flow is exactly that. And what's happened in the picture here is as soon as the smoke comes off of these sticks, it's very warm, and much warmer than the surrounding air. And so there isn't a lot of interaction that takes place when things are very different in temperature, and you end up having what we call this laminar flow. You see the same thing for like cigarettes. You look at a cigarette being burned, and what happens is the smoke initially, as it comes off, is laminar, and then as it gets up, maybe a few inches, it turns turbulent. As it cools down, and then it starts to mix with the air. Well, the turbulent nature of this is as a bit difficult to model, and so we're going to assume that we have laminar flow, so we're not worried about any interactions that are taking place with this environment or actually within itself. So it's just a special condition that we're going to work with here. So laminar flow is what we're considering here. Okay, so one very important principle about this involves the concept of what we call volume flow rate, which is another sort of term for flux. It's a type of flux. Volume flow rate is basically how much water moves through a given area per second. And that is a type of mass conservation, actually, right? When we're saying that our volume flow rate is constant, what we are saying is that the same volume of water has to pass through a given area in a certain amount of time. This is, as I mentioned, sort of a mass conservation argument. Now, the way we express volume flow rate is volume per time. Well, we can take, if you think about like a cylindrical pipe or something like that, we can transform this a little bit. We can imagine that our volume is that of a cylinder, so it's the area times sort of a length. Well, that length can be considered like a dx. There's a dt for time, and we can turn that into a velocity. So a volume flow rate can actually be expressed as a product of the velocity of the fluid times the cross-sectional area that it passes through. And so we can actually take our conservation of mass concept and turn it into what we call the equation of continuity. And what it says is that if we look at like a pipe, for example, or some kind of tube, that the volume flow rate has to be the same throughout. Because if it was not the same, then there would be water building up in places, or it would be leave it in places, like there would be a leak somewhere or something like that. And this is a very common, you'll see this in 120. If you take 120, we have the same kind of principle. It's called conservation of current. Same deal. When electricity runs through a wire, the current, the flow of electrons has got to always be the same throughout, because if it wasn't, charge would be building up somewhere or be removed. Anyway, that's for 120. But so anyway, we have this equation of continuity that allows us to figure out for different cross-sectional areas how fast fluid is moving. And you could see that in the example here with the faucet here. As this water falls, it speeds up due to gravitational acceleration. And so the speed is increased, and so the cross-sectional area of this, and the tube, so to speak, is just water tension keeping the stream together. That's why it thins out at the bottom here. Because it's traveling faster, so traveling faster, in order to conserve the amount of mass flowing through there, you'd have to have a much smaller cross-sectional area. So, all right, let's get into a problem here. All right, so we got a 1 centimeter diameter pipe. It's going to widen to 2 centimeters. Okay, so that means the cross-sectional area is going to increase by a factor of 4. Remember, it's an area, so if you increase the diameter, that's radius squared, so you're actually increasing the cross-sectional area by 4. And then it narrows down to basically a half of a centimeter, 5 millimeters, right? Liquid flows through the first segment at a speed of 4 meters per second, and we want to know what the speed is in the other segments. Now, we do the mathematics here, but the concept is really what matters here. Ultimately, the volume flow, and you can do this for any part here because they all have to be the same. You do the velocity times the area. So if we do that for the first part, you'll get this number down here. Now, the numbers I plugged in here are the numbers for the third part here, but again, they're all the same. All the v times a's have got to be the same. So you simply solve for the velocity in the other regions there, and here's what you see. If you go to the wider pipe, larger area, smaller speed, down by a factor of 4. 1 meter per second squared. If we go to the thinner opening, right, the smaller opening, again, we're down by a factor of 2. For area, we're down by a factor of 4, and so the velocity is going to go up by a factor of 4. Okay, so we go from 4 to 16. Okay, nice concept there. It's pretty simple. Moving right along. All right, so you better not get this wrong. How about that? You better not get this wrong. I just spent all this time, all those 1 or 2 minutes. Water flows from the left to the right through the pipe. What can you say about the speed of the water at points 1 and 2? The answer here is, oops, C, right? The velocity at point 1 is going to be smaller because the area is bigger. Equation of continuity. All right, so this brings us to Bernoulli's equation, which is a conservation of energy statement about how fluid is going to flow through a system, a pipe or some kind, and be under the influence of many factors. There are basically 3 factors at work that we're considering here. We're considering the pressure that is found in this particular area of the pipe. So if we look on the left-hand side there and we look at that area there, we actually have a few things going on here. We have a pressure that's exerted at a particular depth, okay, which we're calling Y1. And so that is a type of like work, basically. The pressure is a force that's pushing on the liquid here. So it's attempting to increase the energy of that portion of water. We also have a kinetic energy here, right? We have kinetic energy of the water moving through the pipe, and we also have a potential energy. And so in the example here, we see that our pipe is going to widen as it gets further up. And so when we get to the top there, we have to consider some different factors here. There's going to be a different pressure potentially up at that point. The velocity of the liquid is going to be different. Equation of continuity helps us understand that. And the water went to a higher level, so it has to do some things against gravity. And so there's a gravitational energy term that we need to consider there, okay? Right, so this brings us to Bernoulli's equation, which is a sort of conservation of energy where we consider the flow of fluid inside of a tube, and we're considering various kinetic and potential energies that are going to change how the fluid is going to move through that area there. And there's 3 factors that we're going to need to consider here. One of the factors is the amount of pressure that exists there, the kinetic energy of the water that moves through there, and gravitational effects. Right? In this example here, the water is moving up to a higher location, and so that means there has to be some kind of work done against gravity, and that will take energy from the system. All right, and so mathematically, we're looking at it like this. The top equation is effectively a conservation of energy, like an initial and a final. It involves the pressure at a particular location, the velocity of the fluid at that particular location. Okay, and this is a kinetic energy term here. Now it's given in terms of rho, so that's a mass over a volume. In fact, what this is here, this is a force. Imagine this is a force, kinetic energy, gravitational energy. The entire equation is just divided by volume, and that changes the first term to a pressure, right? It changes this term into a kinetic energy, and it changes this term here into a hydrostatic pressure. But this should look familiar. It looks just like traditional energy here. So anyway, the first factor here is pressure, then kinetic energy, and then gravitational energy. And so that's our relationship that we're going to work with here. And the alternative form is that you just look at the equation, one state by itself and it equals a constant. But when we handle conservation things, we usually like to do a before and after, or point 1 and point 2. We kind of freeze time and we look at what's going on here. And so that's what we are considering here. Actually, this is a good illustration of Bernoulli's equation here. So what you can do is take a thin strip of paper, put it up to your lips, and put it on your lower lip, and you blow, right? Just blow out air. When you do that, you're increasing the speed of the air. as it comes out. And in order to conserve energy there, by having the air move very fast, it automatically will decrease the pressure in the air. Now, underneath the strip, you don't have that airspeed taking place there. So what you have is you have a pressure differential. The pressure on top of the strip is less than the pressure at the bottom, and that's going to create an upward force that will make the strip rise a bit. Okay, so you can do that. Just cut a thin strip out, put it underneath your bottom lip there and blow, and you'll see that the strip will kind of come up a bit. But actually what you might see is it kind of comes up and it kind of flutters around, and that's the turbulent flow. When it comes out of your mouth, it's warm air initially, and that's going to be laminar, but then as it gets to the end of the strip, you'll see the strip start flipping around a bit. That's a lot of that's due to the turbulent nature of the air as it's exited out of your mouth there a bit. So that's kind of a neat little illustration of that. But one of the biggest things about Bernoulli's principle is this relationship between air pressure and velocity. And when the velocity of the air is great, the pressure drops. And so anyway. All right, so in this example here, gas flows from left to right through the pipe. The interior is hidden, but we want to know which point of the pipe has the smallest diameter. So we can't see that in here, but we can tell by the columns of liquid here what would have to be a smaller diameter for that. So think about that for a moment. And the answer here is B. B has a higher column of liquid, which means that the pressure in that column at the top is less than the other ones. And that would occur if the fluid there is moving at a faster speed. It would be moving at a faster speed if the diameter was smaller. So we're actually combining two things here. We're combining the equation of continuity, right? Establishing that we have a faster speed in a smaller section of pipe. Faster speeds is going to relate to a lower pressure. So in terms of Bernoulli's equation, we're not considering any gravitational energy here. We're just considering pressure and the velocity. So we're mixing those two together, right? The equation of continuity tells us that small diameter is a fast speed. Bernoulli's equation tells us fast speed means small pressure. And we see that in the columns of liquid there. One last example here. We have water flowing through a pipe. We're reading the pressure off on the bottom there. We don't know what the pressure is in the top, but we know a few things about this. We can see that the pipe thins out as we get to the top. We can see that the flow of water increases as we get to the top. And so we're trying to determine what the pressure is going to be up there. Now, as you can see here, we're going to a higher location. Right? Higher location means things might be moving a little slower because of it. But we have a thinner pipe, so things might be moving a little faster. So it's not really clear what we're going to end up with here. Let's just look at the example. Okay, so now you can do both the equation of continuity and Bernoulli's equation in this problem here. And we're going to need to do that because we see Bernoulli's equation right down here. And we have too many variables, basically. We're trying to solve for P2. Well, we have the velocity at point 1. We don't know the velocity at point 2. We have our two gravitational expressions in here. But as you remember with gravitational energy, we choose 0 points. So naturally, we want to choose a 0 point on the bottom here. At point 1 is our 0 point, so we have no gravitational energy there. That's y equals 0. When we get up to point 2 here, we're 2 meters higher, so we're going to call that y equals 2. Okay. So let's first do our equation of continuity. We have our velocity in the first part, and we're trying to look at the cross-sectional areas of these two pipes here. Now, as you can see here, the diameter of the first pipe is 6, the next one is 4. I'm just going to use radii here, so 0.03, 0.02. In fact, these are proportions. I didn't really need to convert them to meters, but anyway, I did. We end up with a speed that is a bit faster, 11.25 meters per second. So that will go into the equation down here. All right, so let's fill out the rest of it. I know the pressure at the bottom here, it's 75 kilopascal, so I got 75,000 in there. We're using water, so that's a density of 1,000. Their speed is 5. On the right-hand side, I'm moving a bit faster here, right? Our gravitational energy, we have a bit of increase in gravitational energy. And so you can see here that this kinetic energy term is much larger than this one over here, significantly larger. But we also have this gravitational point here, but it doesn't really appear this gravitational part's going to be a big deal, honestly. But let's go ahead and just put our numbers in here. We're solving for P2, and when we do that, we get a 4.6 kilopascals. So the pressure is significantly lower, and really that's to a large extent that is sort of due to, well, both these things really contribute to it, honestly. Because look, if you look over here, you have this pressure that's 75,000, and you got this kinetic energy. Well, the pressure goes down, and where does that energy go? Well, it goes into lifting the liquid to some extent, and also goes into making the liquid move a lot faster. So we do expect to have a significantly smaller speed here. I think earlier I might have said that, oh, the gravitational energy may make things go, may things go up, actually. Well, no, I think I might have misspoke when I said that. But both these factors here are definitely making pressure go down. You're taking energy out. Think about it like that. Taking energy out to lift the liquid and make it go faster. So we would definitely, it makes sense that the pressure is lower. How much lower is kind of up in the air, I guess, right? Right, so that's the example of Bernoulli's equation. We went over buoyancy as well. That takes us to the end of fluid dynamics. The next chapter is gravity. That's fun. It's my wheelhouse, astronomy. So I'm going to try to control myself during that lecture and not make the lecture 3 hours long.